Hello, everyone. Can you hear me? Can somebody say yes or no?
Yes, Professor.
Yes.
Thank you very much. Okay. This is a slide that was presented last time when we discussed situation with adding integers. And the reason why we are doing this little survey of numerical problems is that it is very good if you know these things, because you are going to feel very comfortably when you do any kind of computation and you know what is the result that has to occur on your screen. Therefore, this is the reason and motivation for studying this. On the other hand, also, people come from different backgrounds, from community colleges, from different versions of 210 class. This is something that should be presented in introductory classes, but since we have different backgrounds, some people know this, some people don't, so it is better to have this survey given in 600, that we are sure that you are going to feel comfortably with numerical computations of any kind. So the last thing that we showed is that when you compute adding positive numbers, you can get the sum of positive numbers is smaller than the values being added. So this is this example here. You have also that the sum of two positive numbers can be negative. So if you have a short integer, then you have a 16-bit format, and if you add two positive numbers, you get negative result. What is, of course, normal, because we have the ring of integers where when you reach the largest positive value, then the next value is the negative value, and that means largest negative value after this 67 is minus 6. The same situation is when you subtract two negative values, you can get positive result. So we have to be aware of that. And this happens regardless of the format. If you have integers, not short integers, then this is the same thing, just the numbers are slightly different. So again, you can add two positive numbers, like in this example here, and get negative result. And the same is here, adding two negative numbers gives you positive result. So this is expected, it is well known, we are not surprised by doing that, and we can prevent that if we want. There are also prevention of overflow techniques that are used in programming, like in the case where you have to compute and choose k, which is, for example, necessary each time when we compute the response time of a server that is serving n workstations. So if you have a server like a bank server and you have ATMs in the city and you want to compute the response time of each of these ATMs, how long does it take to respond to your request? You want to see your balance, you click on balance, and then you wait until balance comes on the screen. So this time that is critical for the quality of service of bank is computed using, for example, binomial coefficients. And n is the number of workstations or ATMs. And you can have easily that n is 300 that a big bank has in an area. And you cannot compute 300 factorial because this is a huge number. So you cannot compute naively 300 factorials and here whatever is k factorials and divide these things. But if you go zigzag, take this value, divide by 2, multiply by 9, divide by 3, multiply by 8, divide by 4, etc., then you keep this value small in the sense that you have that 10 and 2 cancels. 9 and 3 cancels. So this is 3 times 3. So it is going to be cancelled. 8 divided by 4 will be 2. So if you go zigzag, 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 the value is going to be moderate, and you're going to get correct value. And of course, this is the program where you have the numerator is going from n with decrement, and denominator is going from 1 with increment. And then you put that in a loop and compute that previous value is multiplied by numerator divided by denominator. And in this operation, you are always going to have canceling, and it is going to work properly. Now, if you want to avoid overflow and to detect and avoid overflow, you can do that. So if you suspect that you are going to have to work with numbers that are large, that are going to create overflow in the case of integer arithmetic, then if you suspect that a plus b is going to be greater than the maximum value that you can fit in your memory location, then before that, you can check whether b is less than or equal to maximum minus a. And if it is less than this, then it is safe to perform operation and correct result will be. However, if you have that b is greater than maximum minus a, this is immediately this is proof that the next result will be overflow, and therefore you can prevent that by not performing this operation. Similar situation is in the case where you have multiplication. So if we multiply a times b, this can give result that fits inside available memory, or that creates overflow and is going and creating a wrong result. So again, you can check before that whether overflow will occur or not. Because if you multiply a times b in a correct way without overflow, then when you divide that by b, you should get as the result a again, because b divided by b should cancel. However, if a times b is not correct, then you are going to get that a is different than a times b divided by b. Okay, if there is a question, if you raise hand, please unmute your microphone and ask the question.
I have a question. So for real coding, does your compiler or IDE automatically correct if you overflow a primitive data type? I mean, from long to long, like.
Of course not. Compiler or IDE will do nothing for you, except.
So it is an error. Sorry.
Pardon me?
So when you overflow, it is an error, right, or exception?
Yeah. Well, yes, either an error or exceptions. In some cases, in most cases, for example, all these programs that we had here with wrong results, all this is wrong, this area. But the program is perfectly correct. And this is respectable compiler that I use, all of them, either Microsoft or GNU products. So this is completely legitimate, tiny little program that has 4 lines of code, but this is correct C++, and these are wrong results. So compiler is doing nothing for me to prevent this. This is the reason why we are mentioning this, because if compiler were somehow doing that, it is not possible to predict that, because you don't know what kind of numbers are going to be used, you know. However, if you as a programmer wants to put this test inside, then overflow can never occur. But this, first of all, makes your program longer, makes your program slower, and there is no need for that if the problem is of such type that this is not going to happen. You know, for example, if you are working with probabilities, you know the probabilities between 0 and 1 cannot be outside of that range. So it cannot create some problems with real numbers, for example, that are outside of that range. So it is not necessary to do things like this. But if you suspect that this can happen by some category of users, you write the correct program. Correct is working perfectly okay. But now you give this to a user who is going to enter some data that are close to overflow, and it is creating overflow. So if this can happen in accidental or any other situation, you can prevent that if you want. If you assume that this is not going to happen, you don't use things like this. You multiply two numbers and you don't check whether there is overflow. For example, in all my research that is related to artificial intelligence, I don't have any such huge numbers, so I don't need to use this. But if I were working with some equipment that depends on the accuracy of my result, I don't want to be guilty for making overflow. So you put these things in infrequent situations where you need that. Okay, is this reasonable answer, or you have something else to?
Thank you.
Okay, you're welcome, sir. So, like I said, do not do this each and every time. Absolutely not. But if you want to detect, you know how to do it. So if I want to know, is the multiplication going to create an error, I'm going to multiply and divide before that. And if these two things are the same, then it works correctly. If you have that A times B is not correct value, then when you divide that by B, it is not going to give you A, because A times B was wrong. So you can tell in advance that this here is going to create an error, and you are not going to multiply A times B. Because before you do that, you can say, no, this is not going to be correct result. And is this necessary in each and every multiplication? Of course not. But if you have a situation that you suspect that you might have this problem, you know how to solve it. And that is what we do here. Now, what is the ratio of the size of binary and decimal numbers? By the way, please stop me whenever you want to ask questions. No problem with that. So the only thing that you have to do is to unmute your microphone, and then I hear your voice in my earbuds, and then I stop and you ask question, and then we continue. It is the same thing as in the classroom. Also, if you want to raise hand, that's fine, but you don't need that. Just say whatever you think is appropriate. Thank you. So let's go to see what is the size of binary and decimal numbers. So if I have a decimal number like this, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the number that has 9 digits. So D is the number of decimal digits. Now, all humans use decimal system, but inside computer, numbers are stored as binary numbers. So this number, integer, will be stored in some pattern of ones and zeros. And I have B of them. So the question is, how many bits B you need for these D decimal digits? Of course, if you have D digits and B bits, with B bits, you can make 2 to be different combinations, 2 to be different numbers. On the other hand, with D digits, you can make 10 to D different numbers. So if these two things are equivalent, then 2 to B has to be approximately equal 10 to D. If I take decimal logarithm of this, I get here B times logarithm of 2. Logarithm of 2 is approximately 0.3. So B times 0.3. and logarithm of 10 is 1. So this is equal to d. So the ratio is that number of decimal digits is 0.3 times b, that can fit in b bits. The question, how many bits you need to have d digits, it is 3.3 bits per each decimal digit, approximately. So if you ask me, can I put a 10-digit number inside my 32-bit word of my computer, I will say 10 times 3.3 is 33. And you have 32 bits in your memory word. Therefore, the answer is no, you cannot fit 10-digit numbers in your computer, and that's it. No way you can put it inside. So it is good to know these two little formulas that are telling you what is the size of number that can fit in specific number bits. The same holds for real numbers. Real numbers are stored in memory using two integers. One integer is Mantissa and the other is Exponent. So what we have here is that decimal number is written like 0.987 times 10 to Exponent 3, for example. So if you have a real number 123, then it is going to be here 0.123, and here will be 3 times 10 to 3, and this is 123. So we have two integers that are used for storing the memory in memory the real number. Therefore, the internal format of real numbers looks like this. You have sign, which can be plus or minus, coded as 0 or 1. 1 means that this is negative number. 0 means that this is non-negative number, so either positive number or 0. And then you have here Mantissa. These are binary digits that are stored in this area, and then you have Exponent. Exponent is usually 8 bits in standard precision. So you have here that the largest value that can fit inside is 127. And Mantissa has 24 bits or 23 bits, because if this is 8 and this is 23 and plus 1 gives you, this is 24 plus 8, 32. Therefore, this sign is the first thing, and then after that you have bits of Mantissa. So in computer systems, you have that the numbers are written as binary Mantissa, these are ones and zeros, times 2 to this exponent. Now, it is important to know how big is this and how big is this, because this will tell you what is the range of numbers and precision. Precision is defined by the number of bits that you have in Mantissa. So this determines how many significant decimal digits you are going to have in your decimal number. And E is exponent, and it determines what is the largest value that you are going to have in the area of real numbers. So if we have these two things, exponent determines the range of real numbers, that means minimum and maximum values, and Mantissa determines the precision of real numbers, that means how many significant decimal digits you have in the number. So very frequently you will see in literature and on computer screen huge decimal numbers. So numbers that have 10 digits before decimal point and 15 digits after decimal point. So it is legitimate to ask, are all these numbers correct or not? And usually they are not correct and written simply because whoever used them does not understand how is that stored in memory. Therefore, it is useful to know these formats of numbers so that we know whether we have correct or incorrect things that we present as results. So here is what happens if we have 32 bits and 8 bits used for exponent. So exponent will be in the range from minus 128, which is the smallest value that can fit in 8 bits, and 127, which is the largest value that can fit in 8 bits. So the largest value will be 2 to 127, which is approximately 10 to 38. And the minimum value positive that you can have is 2 to minus 128, because this is the smallest negative value, which is approximately 10 to minus 39. So this tells you that real numbers in your computer have range that is limited. So if you take real axis in mathematics, you have here 0 somewhere in the middle, and then you have infinitely dense real numbers next to each other that are distributed on this real axis. So you have an infinite number of them. Of course, unfortunately, in computer systems, these are points that have huge gaps between them. Practically in each gap, you have an infinite number of values that you cannot present. So you have here 0, and then next point is the smallest real value, which is 10 to minus 39. There is nothing between these two values. So you cannot have any number that is between 0 and 10 to minus 39. You can have either 0 or 10 to minus 39 and nothing else in the case of 32-bit format. Okay, and then we have other values that are distributed on real axis, and then when we come to max real, which is in this case 10 to 39, this is this last dot. So we have to understand that real numbers are these dots, these points along real axis that are going from minus maximum real, which is this point here, to plus maximum real. And that also we have this gap between the minimum negative value and minimum positive value. So here is the gap. So you can say this is the range of real numbers, looks like this. And 0 is, of course, correct in the middle. Is this clear, or any question related to this? Okay, so of course, very frequently 10 to minus 39 is perfectly close to 0, and we are satisfied with that and perform calculations without problems. However, sometimes if you have big values, like for example, if you work in physics or astronomy, then this 10 to 38 is not going to be sufficient, and you need much more. So you need different formats of data if they are supported. So the precision is always given as logarithm of 2 times the number of bits in Mantissa. So the number of significant decimal digits m is 0.30103 times m. And this is the formula for computing how many digits you can have. So if you have on your screen this value here, 98765, etc. Okay, then you know for sure that you cannot have an infinite number of digits. But this here that has 7 digits, because in 24-bit Mantissa you have 24 times 0.3, which is 7.2 significant decimal digits. So in standard precision, we have real numbers that have 7 significant decimal digits. So this is 1, 2, 3, 4, 5, 6, 7. Therefore, this has chance to be accurate and can be stored in memory. Whatever comes after that is random junk that is generated by the algorithm that converts binary 2 decimal. And it works by using the remainder of previous calculation and making next iteration. So it is a loop that is looping and creating digit by digit, but always takes the remainder of previous operation and creating the new digit in that way. So after you exhaust what you have in your memory, after that you create random numbers. And of course, this should not appear on the screen, or if it appears, you have to cut it here to have only accurate values, not values that are not accurate. So what we have in current computer systems is standard precision and double precision. Standard precision, for example, in C or C++ or Java or any language, is that word size has 32 bits. That's the most frequent situation. Mantissa has 24 bits, Exponent 8. Therefore, range maximum real is 10 to 38. And precision, number of significant decimal digit, is 7.2. If this is not enough, then you can decide to use double precision. This is going to work slower and take more memory, but will give you better precision and bigger range, because most of current computers and compilers have in 64 bits in double precision, Mantissa that has 53 bits, and Exponent that has 11 bits. So 2 to 11 gives you the range of 10 to 30 to 308. So this is a rather big number. 10 to 308 is a very big number, insufficient for astronomy, but sufficient in most cases of computer applications. And precision, which is number of significant decimal digits, is close to 16.
Excuse me, can
Yes.
you explain how can you get the range, the number of range there?
Range is 2 to, you have Mantissa of 53 and 11 here. So 2 to 11, 11 bits gives you 2 to 11 minus 1 largest value, 2 to 10 minus 1. So this is this formula here. But you don't have 127, but you have larger values. So if you have 11 bits here, you have 2 to 10 minus 1, which is 1023. So 2 to 1023 gives you this 10 to 308. It is computed using the same formula, just you have a bigger exponent, and therefore the largest integer that can fit in 11 bits is 2 to 10 minus 1. 2 to 10 is 1024. Minus 1, 1023. And then 2 to 1023 is same as 10 to 308. That's how you compute that. Is that the answer that you wanted to hear, or something else?
Sorry, can you explain again?
To explain what?
How can you get the range there?
The range is shown here. The range is 2 to the maximum exponent, maximum value that fits in exponent. Exponent is this here, or this part here of your word. If you have this is 64 bits, then this here, exponent, has 11 bits. Do you agree with that? This is the standard. So there are 11 ones and zeros here. What is number that you can put here? What is the largest integer that can fit in n bits? The largest integer is shown here. If you remember, this is 2 to n minus 1 minus 1. That's the largest integer in n bits. If we have 11 bits, 11 minus 1 is 10. So what is 2 to 10? 2 to 10 is 1024, okay? And minus 1 is 1023. Is this okay?
Yeah.
Okay, so we go here, and we have that the largest value is 1023. So 2 to 1023 gives you the largest value that you can get as multiplier of this number that has largest value 1. So this is the range, 2 to 1023. Now, if you compute that, you are going to get a huge number, which is equal to 10 to 308. And that's what you have in all double precision programs, that you cannot go above that, but to 10 to 308, you can go there with 11 bits of exponent. And 53 bits of Mantissa give you approximately 60 significant decimal digits. Is this a little more clear now?
Yes, thank you.
You're welcome, sir. We have also to mention that there are older compilers and older formats that you might still encounter that take these 64 bits and say, we are going to use only 8 bits of Mantissa, of exponent, but we'll have, because of that, 56 bits of Mantissa. So exponent only 8 bits. So same as in the case of standard precision, you are going to get that the maximum real will be 10 to 38, but you have now more bits in Mantissa, and precision will be 16.8, let us say 17 significant decimal digits. If you compare these two formats, you will see that this is negligible improvement. If you have 16 or 17 significant decimal digits, nothing good will happen, okay? But you lose huge range. So the difference between 10 to 38 and 10 to 308 is huge. So this is not good format. And if you encountered somewhere, be advised that this is much better. And this is what we have currently in all C++ compilers and in all IDEs that are using formatting of data in this way, and processors are supporting this. So this is in most cases, but you can still somewhere find this. So I want you to know that this is also possible. But in 95% of cases, you are going to encounter this situation today. Now, imprecision of real numbers is something that is important to know. If you divide, for example, 1 divided by 7, then you get both in decimal system and in binary system a number that has an infinite number of digits. If you have an infinite number of digits, then you have to truncate them or round them and put them inside your memory where you can fit them. Therefore, the number that is stored in memory can be either less than 1 divided by 7 or greater than 1 divided by 7. But you cannot have 1 divided by 7 because this needs an infinite number of digits. Therefore, if you write a program like this one here, where I have a do loop in Fortran that is going from 1 divided by 7 to 1, with step 1 divided by 7, and I'm writing this x. So I'm going to get 1 divided by 7 is 0.14, 2 divided by 7, 0.28, and so on and so forth. But I'm not going to get 1. So this here is 6 divided by 7, but 7 divided by 7 is not printed. So what is the reason for that? Because I want to go with step 1 over 7 up to 1. And the reason is very simple to explain, that you have that 1 divided by 7 after converting to binary is giving something that is a little bigger than 1 divided by 7. So when you add 7 times this, what is a little bigger, you get something that is slightly bigger than 1. And therefore, you terminate the loop because you are going above the limit of the loop, which is 1. And therefore, you don't get this last value. So you will certainly encounter things like this because very, very frequently we have that the binary number is simply infinite. For example, if you have that step is 0.1, so 1 divided by 10. 1 divided by 10 cannot be stored in computer memory at all because it has infinite number of binary digits. So you have to cut that to a format of either 32 or 64 bits. And then when you cut that, you get either something that is a little bigger or a little smaller than 0.1. And you have to understand that this is going to happen. Here is an example that shows this kind of problems. I have this loop where I want to display the tangent of an angle. So I go with angle from 0 to 1 and then multiply that by pi divided by 2. So when this is 1, pi divided by 2 is 90 degrees. So if I have that x is 0.5, I should get that the tangent is 1 because this is triangle that has 2 equal sides. Therefore, tangent is 1. What I get here is 0.999999, but the rest is random junk. So I get only 5 significant decimal digits that are correct. Okay, the rest is completely wrong. Not only that, but when I come to in this loop that is going from 0 to 1, if I get that x is 1, then I should get infinity because the tangent of 90 degrees is infinitely large. What I get as a result is not infinity, but 788,000. So what kind of infinity is this? This is very miserable infinity because it is 780,000. So what? What is the reason for this wrong result? Of course, the reason is that my pi is not sufficiently correct. I have the pi that has 6 significant decimal digits. But this is a typical example. I can put here more or less, but you are always going to have the same thing. So neither this is correct nor this is correct. Both of them are close, but this here is maybe tolerable error. This one here is tragical because you have to get infinity and you don't have it. This is what happens always when we do numerical computations, and we have to be aware of that. Another thing that is encountered frequently is that in the case of real numbers, addition is not commutative. So if you have a plus b plus c, this is not the same as c plus b plus a. Now, you can think, you know what, in mathematics, a plus b plus c is always equal c plus b plus a, because this is commutative operation. The order of addition does not change the result. Well, this is not the case in computer systems. In computer systems, only if you add 2 numbers, you are always going to get the same result. But if you add the third one, then it depends on the order of additions. What are the first 2? In what order is this going? So if you go a plus b and then c, this is different from c plus b and then a. So what is the reason? Well, because if you add a large number and a small number, then you have to align decimal points. And if this small number is very small, a part of it is going to be simply truncated and cut, and you are not going to have it, making problems that are going to be visible. So are not always commutative. To show you example that shows explicitly what happens is example, I want to add harmonic series. So 1 plus 1 divided by 2 plus 1 divided by 3 plus 1 divided by n. And this is going to give you some numeric result. But I can compute the same sum going from small values towards big values. So I have here 1 divided by n plus 1 divided by n minus 1 plus 1 divided by 3, 1 divided by 2, and 1. So these are two identical sums. And I'm computing them here inside this loop as increasing sum and decreasing sum. So increasing sum is 1 plus 1 divided by 2 plus 1 divided by 3. So this I is 1, 2, 3 up to n. So starting with 1 plus 0.5 plus 1 divided by 3, etc. And here I'm going backwards. 1 divided by n, n minus I plus 1, float 1. So I'm going to get, I work with float values here. So all of them are float to have standard precision. And what I have that these two sums that mathematically should be identical are different. So if I go 1 plus 1 divided by 2 plus 1 divided by million, I'm going up to million, I get 14.35. But if I go in opposite direction, I get 14.39. So the question is, which first, why they are different and which one is better? And not only that, but I see that this accuracy is just 3 digits because 1, 4, 3 is both here and here. This is now questionable, this 3 digits and 3 digits. And they are still presented here as if they were correct, and they are not. This here is better. Why? Because when I add two small values, they are going to be close to each other, and bigger part of those digits are going to participate in creating this sum. So when I come to the end, when I have to add this to 1, I'm going to have more precise value here than I have here. Because if I have 1 plus some very small value, for example, in standard precision, where I have 7 significant decimal digits, if I divide by something that is 10 to minus 8, it is not going to take into account at all. So this value here is greater than and more precise than this value here. So if you write the program where you can decide to go in increasing or in decreasing sequence of terms that you are adding, it is better to go in the increasing direction, adding small numbers to bigger numbers as opposed to add bigger numbers to smaller numbers. The results are going to be different, and one that is going in increasing sequence will be more accurate. And this is proved here. Write this program on your computer this afternoon, and you will see similar results.
Professor?
Now, I have here a little more. Yes, sir. Yes,
and
please.
This is the case for all programming languages, since it's the
of course
built-in.
Of course.
Okay. Interesting.
Yes, yes. For all programming languages, all computers, wherever you move, you have this kind of stuff. But of course, if you don't have always that you add million numbers, and not always that you have increasing or decreasing. So if you have random numbers, that you are adding, you might say, you know what, I'm going to sort them, and then I'm going to add them from the smallest to the biggest. Well, this would be dramatical, because if you have to sort million numbers, this is going to take some time. So you slow down your computation for some miserable increase of accuracy that maybe it is not important in your calculation. So you are not going to do this at the expense of making things more complex. But here, in this example, it is equally difficult to go in one direction or the other direction. So you have either this line of code or this line of code. So it is completely the same. I will take one of them and will not make this program slower, but it is going to be more accurate if I go in this way. And this is going to be in all our beloved languages, Python included, Ruby included, Java included, C++, all of them. So unfortunately, it is that way, because this is the property of finite size of memory locations. You cannot have infinite precision inside, obviously. But it is good to know how wrong is this going to be, so that you can be prepared to prevent that if it is necessary to think about these things. That's why we spent these 75 minutes on these problems. This here is exactly the same thing, just an expanded example that also for all these sizes shows different results. Here is this 1435, 1439. Now you go to 10 million, you get here 15, here 16. And here 15, here 18. So bigger and bigger differences as more and more errors you accumulate. Obviously, if you have huge number, then the difference will be big, simply because it is truncated completely. A big number plus very small number is not changed. It is just the same big number, same as adding 0. So that's the problem. So observation from this experiment is that in most cases, decreasing sum is greater and more accurate than increasing sum. If n is small for this harmonic series, like less than 1 million, all results are similar. But if you have towards bigger values, so if you have n greater than 10 to 8, float sums remain constant and significantly incorrect. Okay, so this is the way it should be. But if we know this, we are prepared to have that, and then we try to compensate that in a variety of ways. Another thing that is necessary to know is the ASCII table, because we frequently work with strings and with characters. Not only that, but we use characters for storing small integers that can be signed or unsigned. An ASCII table is this one. It has 4 columns. These are 4 columns. And the first column that has 32 values, there are a couple of values that are important and should be memorized. First, 0, that is coded as 8 zeros, is called null. Null is the very well-known terminator of C strings. So if you have a string that has null at the end, then you can easily compute the length of the string. And I'm not speaking about string objects. I'm speaking about C strings that are terminated with null. Another very important thing that we need to know is line feed, new line. New line is coded as 10. And another important thing is 7, which is the sound signal. So if you print 7 on your screen, character 7, you are going to get acoustic signal, beep or dong or something like that, which I hear in my earbud when somebody enters or exits this lecture. I hear always ding, and I know that you went out or you came just. This is visible, and I can hear that. You have here also important thing that is 27, that you use every day many times. This is escape signal. When you press escape button of keyboard, this is generating 27 as the code that is important. Now, these other codes are for communication. For example, 13 is carriage return. If you want to move a cursor on your screen from wherever it is in the line to beginning of that line, if you send carriage return signal, which is 13, it is going to move cursor at the beginning. Okay. If you have printer, 12 is form feed. So it is going to take the new fresh page. So going here to the way how characters are coded, 0 is coded as 48, and then you add 1 and you get 1. So 49 is 1 and 57 is 9. The same situation of sequencing these values is with characters. So capital A is 65, capital B is 66. So since this alphabet is sorted, then alphabetic sort is done by the same program that is making numerical sort. And of course, all digits are coded also by ASCII characters as 48, 49, 50. One interesting thing is that even numbers are even. For example, digit 2 is given as even code. So you can test even code and know whether the digit is even or odd. In the case of uppercase and lowercase, you have that the uppercase is obtained by taking lowercase and subtracting 32, because you have 32 numbers in this table. So it is important to know this table and how to learn this table. It is very simple. You have just few things. Line feed or new line is character 10 decimal. Bell is 7. And then you have that digit 0 is 48 and capital letter A is 65. And if you know these things, you know everything, because you can always compute what is a lowercase value by adding or subtracting 32 in ASCII. So you have to know that A is 65, and you need to know the 0 is 48, and that's all. Very simple. Maybe to know this 10 and 7, and null, everybody knows that null is 0. So by learning these few things, you know the whole ASCII table. It costs nothing, so it is not good if you don't know these few things. Now, going to conversion from upper to lower, you can say lower is upper plus 32. And this works for American Standard Code for information integer or interchange, what is called ASCII. But if you use EBCDIC, which is extended binary coded decimal interchange code, then it is better to use formula lower is A plus upper minus capital A. This works for each and every kind of coding, because if uppercase is, for example, character A, then A minus A is 0, and you're going to get lowercase a. If this is B, it is going to be A plus 1. So this is going to give you 1. A plus 1 will be B, and lowercase will be B. So this here is safe way of converting lower to upper and upper to lower. And here with 32, that works only for EBCDIC, and I do not suggest to use this, but use this as a better way of doing the same thing. So let us see a little bit of those quiz that we had posted on iLearn, that are questions and answer, that is testing whether we know basics or not. So the first question was, you have unsigned integers A and B that are positive. Can we claim that in all cases A plus B is greater than A? Of course not. These are unsigned integers, and the largest value is 2 to n minus 1. We discussed a minute ago that if you have these 11 bits, that the largest value is 2 to 11 minus 1 for unsigned integer, for signed integer 2 to 10 minus 1. Therefore, you have that above this value, you are going to get the result that is less than A. So the answer is no. In cases where overflow can occur, you must provide code that prevents these wrong results. The second question is, if you have integers, A and B, that are positive, can we claim that in all cases the sum of two positive numbers is positive? Of course, we've seen several programs where this is not the case. Therefore, the answer is no. For machines that have n-bit word, the largest signed integer is 2 to n minus 1 minus 1. And the smallest value is this one here. So if we add two values that are greater than this, we get immediately negative numbers. So it is perfectly possible to get a negative number if A plus B is greater than this maximum value, 2 to n minus 1 minus 1. Here, that's the maximum value. Because we have this ring of integers, and if you go from largest positive value, you jump immediately to smallest negative value. So that is not okay. If we have two negative numbers, so integer a and b, can we claim that in all cases the result of adding two negative numbers will be negative? Of course not. Simply because adding two negative numbers, if you come to the smallest negative value, you jump to the largest positive value, because this is the ring of integers. Therefore, we have that the answer is no. For double x, so we have double x and it is positive. Can we claim in all cases that 1 plus x is greater than 1? Of course, we cannot, because this x can be small, and addition of 1 plus a very small value will give you simply 1 as the result. So you can frequently have that 1 plus something remains unchanged, because this 1 is, for example, in standard precision, stored with 7 significant decimal digits. If you have something that is, for example, 10 to minus 9, that needs more digits, it cannot fit. And when you add these two things, is same as adding 1 plus 0. So to persuade you that this is correct, I wrote here one tiny little program that is adding 1 plus x. And x is in each iteration divided by 2, becoming smaller and smaller. And then if 1 plus x is greater than 1, I'm going to print that it is greater. Otherwise, I am going to say that it is not greater. And this little program you can write for your compiler for your language that you prefer. You're always going to get that 1 plus 0.5, of course, is greater than 1. 1 plus 0.25 greater than 1. But when I come to 1 plus something times 10 to minus 16 is greater than 1, but next one is equal to 1. So if you have this 1.11 times 10 to minus 16 plus 1, the result will be 1. And for all other of them here is going to be 1. There is not going to be sensitivity that can tell you that 1 plus something is greater than 1. It is equal to 1. And so if you have if statement where you are branching depending on whether a value is greater than something, and you compute this value as 1 plus some other value, and you know that this is positive, and you know that this has to be greater than 1 because this is positive, it is not going to happen. So be advised. This usually happens in if statement when you branch to the wrong direction and create all this wrong result, and you know that it should go in different direction, but it is not doing that because of this, that 1 plus x remains 1. Then this previous question, whether a plus b plus c is equal c plus b plus a. Well, we have seen this example when we used harmonic series, and we found that the results are different. Therefore, the answer is, can we claim that in all cases a plus b plus c is equal c plus b plus a? The answer is no. No, the addition of real numbers is performed without commutativity. So not always, of course, and not always critical, but that may yield non-commutativity. A trivial example here is if I have two significant decimal digits to show that if I are adding, for example, 0.12 and 0.06, this is going to be insignificant because this 0.06 with 2 digits is going to be 0, 0. Plus this 0, 0 will give you simply 0.12. So it is not going to make any significant change of that. What is happening here, if you have 0.5 plus 0.6, this is going to give you 0.11. And with 2 digits, you are going to have this 1 plus 0.12 is going to create 0.13. So going in direction big plus small will give you this value, and small plus big we give you this value. These are two different things. So pay attention that is always happening. Of course, we have more than two digits, but again, the behavior will be the same. This one is interesting. It says f equals 1 divided by 3. Real 1 divided by real 3. And the question is, what is going to be printed by this cout? We are asking, is f equals 1 divided by 3? Is this going to be same or different? So I just inserted 1 divided by 3 in f. And I have f is 1 divided by 3 as a question. If you are naive, you would say, of course, f is 1 divided by 3, so here is this 1 divided by 3. The reality is different. This is different. So what is displayed? Explain the reasons. Well, explanation is very simple. These are two very different things. First of all, this f is floating point number with 32 bits. So when I compute 1 divided by 3, this is double precision. And 1 divided by 3 has 16 significant decimal digits. So it is stored as 0.33333333, whatever comes here. On the other hand, this float has only 7 significant decimal digits. So this guy f is 3333333. It has 7 digits here, and this guy has 16, and it is bigger. So when you compare these two things, of course, compiler will convert this to double precision, will subtract these two things, will find that they are different, and will say different. It is not the same. Okay. So these things are understandable if and only if you know how these things are coded in memory. What are data types and data formats? If you don't understand that, you will never know what is going to be printed here. And of course, I want you to feel comfortably and to say immediately, this is different. Okay, and that's why we studied this. Now, we have sign character. We want to watch the small values and say C is 128. After that, we display integer of C and say, show me what is displayed. Displayed result, of course, is not going to be 128. It is going to be minus 128. Why? Because sign character is a character that has the largest value, 127. And then if you add 1 to 127, you come to the smallest negative value, 1 minus 128. So if I put here 128, this is going to be 127 plus 1. And what is going to be displayed is this value here, minus 128, not plus 128. Try it and you will see that it works that way. Then here is the story, what is going to be printed same as or different if I'm adding 1 divided by I to the 3rd degree. So this is a quickly decreasing series of numbers. It is not like this case of harmonic means, but it is very similar. Now I put here I to the 3rd degree. If I am adding this in increasing and decreasing order, these are going to be completely two different numbers. And if I ask, are they the same or different, the answer will be different. So this is the question on quiz, for example. Tell me, is this the same or different? It is different, of course, because I have here 2,000 values, so it is enough to create different values. And indeed, increasing sum and decreasing sum are different. They have here 1, 2, 3, 4, 5, 6, 7 digits that are the same, actually 6, up to this 5. And here you have 0, here you have 6. So from here on, they are different. So increasing sum is greater than decreasing sum, as it should be, as we expect to be. But they are not the same, okay? And what we get here is different. So be prepared that this is going to happen and act accordingly. If you need more accuracy, then take one that is more accurate. If you need something else, then always there is a trick that we can use to control everything. Constants 1, 1, 1, and 1 need the same space in memory, yes or no? Oi, oi, oi. Of course, it is no. Why? Because 1 with dot is a double precision constant, so it takes 8 bytes or 64 bits, and it has sign, mantissa, and exponent in memory. 1 is an integer. Integer takes 4 bytes or 32 bits, and it is written as 00001 at the end. This here is a character. Character 1 is character 0 plus 1. It takes 1 byte, and in ASCII table, 8 bits are going to be ASCII value 48 plus 1, which is 49. But if I have string, this is not string object, but C string. C string is the character 1 terminated by null. Therefore, I'm going to have 2 bytes or 16 bits, and in first is going to be 49, and the second will be null. So this is the string that has 1, and after that, null as terminator. The next question is this: when we display 1 over 3 with 20 digits, all digits after the decimal point will be 3. So that it is going to get 13333, 1 divided by 3. Yes or no? Answer is no, of course. For what reason? Because the constant 3 has the type double, and 1 divided by 3 is also double. So it is having 16 significant decimal digits. So if I force this with set precision to give me 20 digits and display 1 divided by 3, for Microsoft Visual C++, I get 0.333, but after that junk 1, 0, 0, 0. So this is incorrect. It should be 3333, but I get something different. Therefore, you always have that you get only that many digits that can fit inside your memory location, and this is double precision. More than that, you cannot have it. A decimal number has d digits. Show how many bits are needed for storing that. Well, the formula is with the digits is 3.3 times d. That's the formula that we derived a minute ago. Mantissa and exponent. What is mantissa? Mantissa is this string of decimal digit. Exponent is this value here. Okay. And in binary case, we have that this is assumed to be 1. So practically, we have that even if 32-bit format, we have 24 bits of mantissa. Typical data format in bits are 32, 64, or 80. But if you have more, then it is software implementation. This is not implemented by hardware. So you can go with hardware up to 19 digits if you have 80-bit formats for intermediate results in x86 architecture, and you have typically with 11 bits of exponent, you have 16 decimal digits of precision. That's all what you get. Power function is interesting because if you have a real number, then we use that power is computed as exponent of b times logarithm of a. So you have to be careful not to put here base that is negative. So if you have -2 to 3.0001, you're going to apply this formula, and logarithm of -2 is going to explode because this is not defined. Logarithm is only for positive numbers. So practically be careful that if you have that the exponent is an integer value, you are going to get multiplication 2 times 2 times 2. In all other cases, you are going to get exponential of logarithm, and be careful for that. Of course, many modern compilers will take this 3.0 and will say, hey, is this integral value or not? And in this it is. It is not a real value, but it is an integer value. So it will use multiplication. So it is not going to explode. But if you put a little more, it is going to explode. So be careful about that. This function, in the case of C, must have double, double, double. All these other things are available in C++. So C is a very important industrial language for professionals, but pay attention that in C, power function must have the base and exponent and the type of power function double. In the case of C++, you can have whatever you want, long, double, or integer, and these combinations that are shown here are possible. What is going to be displayed by this program? Of course, you have correct pi, but it is not stored in more than long double. So long double gives you this number of 19 digits, and the rest is going to be junk. What is the long double of pi is, of course, limited, and it is shown here. So, summary of numerical problems. Range of all numbers is limited. This holds for unsigned integer, signed integer, and real numbers. The sum of unsigned integer can be less than the numbers being added. The sum of positive integers can be negative. Sum of negative integers can be positive. And the range and precision of real numbers are limited, as we studied. Now, addition of real numbers is restricted by truncation errors. If you have 1 plus x, this can be 1. And then be careful not to put that in an if statement. The sum of real numbers depends on the order of addition. There is no commutativity. And power function is computed using exponential and logarithm. So be sure that this a is a positive number. Okay. So these are basic things of numerical formats, and I hope that you will feel much more comfortably after reading these things, so that you know what you can expect when you perform your numerical calculations. Is there any question that I could answer now? Go ahead. Please unmute your microphone because I cannot hear you now. Unmute the microphone.
Sorry,
because...
can you explain how fraction number stores in computer?
Fraction number are real number divided by another real number. Now, if you have, for example, 1 divided by 3, if you have 1 dot divided by 3 dot, which is this example here. Where is this example? Here is 1. 1 divided by 3. This here, 1, has how many? 64 bits. 3 has 64 bits. Now, when you divide this, you get 0.33333 up to 16 these digits. And this is stored in memory as Mantissa and Exponent. Exponent is 1, and Mantissa is this 0.33333. So when you get this, this is truncated to this 56 bits that is available for that. You don't have more, or 53 bits if you have 11 bits of exponent, as we usually have in double precision. So if you want these 1 and 3 to be float, you have to write 1.f and 3.f. If you write in this way, by default, in all languages, this is considered double. To provide better accuracy, it is assumed to be double. Now, if you put this double in float location, you are going to cut that, and you are going to lose all these 3's that come after these 7 of them. And therefore, it is stored as a value that is either less than or greater than 1 divided by 3. 1 divided by 3 mathematically has an infinite sequence of 3s, so 0.33333 up to infinity. But we can put only 7 of them in memory location. So what is going to be the result? You have value that is less than 1 divided by 3. And if you have more bits, it is going to be a little more precise, but exactly the same thing. And it is not going to be correct. But of course, the errors that are made here are frequently completely acceptable, so that's not a big deal. Is this what you wanted to hear or something else?
Yeah, thank you.
Okay, you're welcome. Any other question? If you have some other questions, please come to office hours. It is from 1 to 2, Monday, today, Wednesday, and Friday. So thank you very much. That's all for today.